Today, in ENGR210-F, the best version of this class you will have this entire day. I just wanted to practice a little bit more before we kind of go into the topics part of the class. By topics, I mean we just cover a couple of odds and ends that are good things to have in your back pocket, but aren't necessarily needed for the final project, if you will. If that negates their value, don't take it that way. There are items of significant importance, but I want to put the focus more so on kind of congealing the skills that you guys have built up over the course of this semester. So what we're going to be working on today is looking at a homework problem that we had done. A lot of folks seem to have trouble with it, so I wanted to go back to it and see what we could do with it. It's looking at plotting the residual of from a numeric analysis. So let's have a look. Bring up a whiteboard. Cool. All right. So what are we talking about? So in the homework for problems, whoops, which you've had to use fixed point iteration to solve a couple different problems. Kind of the one of choice has been this shrinking pellet problem, which I like way too much. But as said, you can apply this to anything. You just need to be able to solve for x in terms of x, if you will. I know that for problems in some of my classes, you have to do something like this, either in Excel or Python, because there are a lot of problems that just don't have analytic solutions, especially the interesting problems. So we start off with this. We said, okay, well, we want to find the radius of the pellet, r, at a particular time t. So we said, like, okay, 5,000 seconds, find r, right? So in order to do that, first we have to cudgel this equation into a form that lets us use our iterative method to do that. So as said, that means we have to solve for the radius. And since we can't solve for the radius analytically, meaning we can't just get r by itself, we have to solve for it implicitly. And that's kind of the point of the iterative method. So in this particular case, we're going to solve for this r. Okay. So I figured I might as well just go through this from the beginning then. So please pardon me if this is extraneous to your experience. Just bear with me here. So first thing, let's get all of this guy over on the left-hand side. See? So something like that. Cool. I'm solving for this particular r. So I need to try to get that guy by itself. So let's see how I could do this. We've been smart to do this in OneNote instead, but oh well. We're already in motion. So if I try to get that middle term, the 3r over r naught squared by itself, let's see, that would look something like that. Okay. work out the rest of that. Take it a step further, solve for that r on the left-hand side. So gives me what? Multiply through by a third. That. The last step's just, well, there's a square there still. Taking the square root of everything, multiplying by r naught, right? Cool. So r equals, excuse me, r naught times the square root of 1/3 6 dE CA0 over rho C r naught squared phi time minus 1 minus 2 times r over r naught cubed. So that is our equation. It's you solved it for r in terms of r. You just picked one of the r's that we had in the equation, said we're going to solve for it, we did it, and that's what we're going to stick into our iterative method. And that's what you guys have been doing for at least a couple of the homeworks now. Okay, so we're going to implement that expression. I'm also going to write it down quick so I don't forget it. So we're going to take that expression and build our iterative method around it, and then we'll look at, okay, what does finding and storing the residual and plotting that look like? So got kind of three steps here. First one is make a successful iterative method, test it, make sure that it works. Second, store the residual, because that's what the residual history is. What the residual is at each iteration is the definition of the residual history. And then we want to plot that. So got three things that we want to try to do. So let's be about it. So compute. Okay. All right, so that's what we are aiming to do. So we're going to be doing math. We're probably going to be using arrays. We know that we're going to be plotting things. So let's get some libraries imported right off the bat. Okay, so first things first. Let's get our inputs. Bless you. So that's our equation. Time we know is something that we specify, but everything else in there is a constant depending on the experiment, right? Time is I want to know what the experiment does at time whatever. The rest of the stuff are constants. So Let's get what those are. Any chance someone has that assignment close to hand? Nope. Okay, I'll just pull it up then. All right. So row C, 0.189 moles per cubic centimeter, R naught, 0.1 centimeters. Phi is 0.5, dE 9.5 times 10 to the negative fourth centimeters squared per second. Ca0 1.4 times 10 to the negative fifth moles per cubic centimeter. Sweet. All right, so let's put that in. So I'm going to put them in here just because I'm not focusing on how to get how to get them. So that's row C. R naught, we said 0.1 centimeters. Phi is 0.5, it's non-dimensional. dE, 9.5 times 10 to the negative fourth centimeters squared per second. Ca0, 1.4 times 10 to the negative fifth moles per centimeter cubed. All right, so those are all of our constants. Know that for the iterative method, we're going to have to initialize some variables, like the rate, literal, like the radius r. Make it 0.09 centimeters just because I feel like it. Set the residual equal to something. We need a convergence tolerance. Set it to that. Okay. Any questions on this stuff? Oh, right. Sorry. Row C is 0.189 units of moles per centimeter cubed. R naught is 0.1 units or centimeters. Phi is 0.5. It's a non-dimensional value. dE is 9.5 times 10 to the negative fourth. Its units are centimeters squared per second. Ca0 is 1.4 times 10 to the negative fifth. Its units are moles per centimeter cubed. I've initialized the value of radius to 0.09 centimeters, value of residual to 1, and so set my convergence tolerance to 1 times 10 to the negative 15th. Good. IGME, any number, I just set it to 1. Yeah, because the next thing I'm going to say is while residual greater than tall, right? That's how all of our iterative methods start. So I just need a value that gets me into the loop. All right, so what do I do now? What do I do now? Yeah. Okay. Yep. Yep. You're absolutely, you're absolutely right. I spent a bunch of time working out this equation. Spent a lot of time solving for r in terms of r. So I need to put, so I did this so that I could stick this into my fixed point iterative method and solve for r. I can put a value in for r, I get a new one for r, and just keep spinning that until I get the same value. I get pretty much the same value twice, or not, or in other words, the difference or the residual between the r I put here and the r I get here is less than my tolerance, which in this case is 1 times 10 to the negative 15th. This also means I need to pick a value for t. I need to pick what time I'm solving this at. So in this particular one, we'll select time is equal to 5,000 seconds. Okay, so equation is r equals r naught times square root of 1/3 times 6 times dE times CA0 over rho C times R0 times, whoopsie daisy, R0 times R0 times phi at times time minus 1 minus 2 times R over R naught cubed. Now, I did see someone do a really neat trick with this, because you know that this guy here, this 6dE times CA naught divided by rho C times rho naught squared times phi thing, that's never going to change value, right? It's essentially just one big number that just sits there. It's a big constant. So if I wanted to declutter this line, one way to do it would be to take that whole expression here, grab that, compute it once prior to the loop, and just use that that value to there. Because I know that it's not going to change. So it can make my efforts reading what I've written a little bit easier. So that was a neat trick that someone did. Now, the one thing I want to change about what I've done here is that I said that my residual is the difference between the r that I put in on the right-hand side of this equation and the r I put in on the left-hand side of the equation, right? So I need to have both of those at the same time. Do I know the value of both of those, the r that I put in here and the r that I put in here? Do I know both of those separately right now? No, because they're both the same. They're both the same variable. So whenever this line gets computed, whatever this guy was is lost because I just wrote over it. So I want one of these to be a different variable. So I'm just going to call this new r. So from that, I can figure out my residual. It's just the absolute value, new r minus r, and keep on going with life. If I do that, in theory, that should give me something good. In theory. So just on the last couple steps that you all have done at one point or another, which is get the residual, set my R equal to whatever I just computed, and just keep that loop going until residual drops below my convergence tolerance. You all on board with that? All right, so let's do a quick check. Let's ask this to print out the radius of the pellet in centimeters. Use a format statement so I can control the output a little bit. I'm having it print the radius of the pellet to five decimal places. So that's a curly bracket, colon, period, 5F, close curly bracket in that little thing there. And I'll insert whatever's in my format statement, right? So let's hold here for about a minute. All right, pop out of this. And that, see what happens. Well, that's not good. Hey, come back here. So, what's that? Yeah. So that means that some math occurred that led to like a square root of -1 or divide by 0 or something like that. And it's saying that ain't a number. Conveniently, Python yelled at me first, said on line 23, specifically this line, you got done screwed up. So there's a pretty good chance that I did my math wrong. So I'm going to cheat and look at what my equation looked like for this, and one that I know works. So I just want to get to the point. Ooh, which one is this in? I think it's in this one. Nope, not that one. Calc. Explain this one. Yeah. Oh, didn't do that. Bother. Have too many programs open. Bother. All right, well, just redo the math quick. Move this over. Yep. 9 by 3. Or not times that. Okay, let's make sure I put this in right. Not times square root. E CA0 row R not phi, good. Constant times phi minus those two. Oh, bother. See if it's just a, oh, that's weird. Must be something earlier. So I'm going to just print off everything. Okay. Still get betting that it's coming out to be a negative number in the square root. Oh, I'm dumb. Should be a negative 1, 1, 1, 1/3. There we go. All right. Now we're cooking. Now we're cooking with grease. So we're moving. Probably don't even need this now. Yep. Great. All right. So we have our method. It works. We've remembered our negative signs. We have our residual. Great. We are here. So now what? Now we move to the second thing that we have to do, right? Which is store the residual, store the value of the residual from iteration to iteration, and also store what iteration that we're on. So first thing, we need to count what iteration that we're on. So how do we do that? We know that the while loop takes time, right? It takes time to solve. For example, if I print out the value of the residual and R on every iteration, so I have my print statement inside of the loop, I just want to, every time the loop runs, I want it to print the value of residual and the radius, right? So if I do that, I get all this. One line for every time that it goes through the loop. So it takes many iterations to come down to the actual answer. That's what you call it. And that's something that I'm going to have to deal with. Rather, it's something that I'm going to have to figure out how many it does. I'm going to have to count them. So it's called how can I get something into that loop to count upwards every time that the loop runs? How can I keep track of how many times that loop spins around? Yeah. I could store things in an array, right? And then I could count and I could look at the size of the array later. It's definitely one way of doing it. But I might as well just count it while I'm going, because that information is what I'm going to want later on when I plot the convergence history or the residual history. I'm going to want I'm going to want that iteration number, or what iteration was it? What time through the loop was it when the residual was blah? So I should count as I go. Okay, tell me what to do. Okay, so the counter's been started at 0. Yep, great. Okay, so counter goes up every time that I go through the loop now. So if I print counter and residual, should get the iteration number that I'm on, as well as the residual that I have at that iteration. There we go. So iteration 1, residual is 0.007, next one's 0.071,
so on and so forth until it's down to 6.5 times 10 to the negative 16th on iteration 55. Great. All right. Now I want to store it. The problem is, I mean, okay, sure, I just saw that it took 55 iterations for t equals 5,000. T equals 3,000 takes 78 iterations. For t equals 1,000, takes 145. I can't predict how many iterations it's going to take in order to solve this problem. Yeah. Mm-hmm. Okay, great. So you absolutely can do that. So for those who might not see what Tom's saying, I could take all that code that I just wrote, paste it a second time, and right before I start that second loop, I've already counted how many iterations it takes in order to do the time and the equation that's in this loop up here between lines 23 and 27. So I can just say, hey, storage array is exactly the size that I need it to be, right? That is an entirely legal thing to do. And actually, I'm going to call this residual store. I'll make another one like it. It's radius store. That is an entirely valid thing to do. You're right. It is tedious because it takes about twice the amount of time to do. But it's something that you definitely can do. It's kind of like when we did, when we were playing around with reading text files the other day. We didn't know how big an array should be when we started reading the text file. But we can go through every line of the text file, count how many there are, close it, make an array that's the right size, open the file back up, and then store everything. This is an entirely valid way to do life. So you can do this. Technically, I don't need time, don't need the constant. Counter doesn't really mean anything down in this one. I'm just storing. Well, it does mean something. I'm just storing everything in this loop. I still need the count. I still need a counter in this loop because I need to tell the arrays where to store information. Right? And the trick is that the counter has to do exactly what it did in the first loop. It has to increment each time the loop goes through. So you store the new information in the next available slot. So if you do something like that, that should work out pretty well. So we can, just for kicks and giggles, can try printing those out. I'll just print out the residual store. Let's see what that does. Well, that's not good. What happened there? That's the value of residual store, right? Whole bunch of zeros. What happened? What numbers? Like const? Let me just comment a few things. Where are you going? So resid store, the thing that I printed out, it was all zeros, right? Well, I initialized it to be zeros. So it's like it didn't change after line 32, right? Okay.
So let's call, so something stopped, something made this essentially not run. Because if line 37 had run, then a value of resid store would be not 0 because residual is stored in resid store. So what would cause line 37 and all those other lines not to run in that while loop? What would cause that while loop not to run? Strictly speaking, the while loop will only run if this is true, right? Yeah. You're right. So we just finished a while loop, an identical while loop up here. And it's in the condition to run this loop was residual being greater than tall. Well, eventually it exited that loop, right? It finished. And so residual, by the time I get down here to line 32, residual is less than tall. Residual is less than my convergence tolerance. Line 33, it's still less than tolerance. Line 34, residual is still less than tolerance. Line 35, it's still less than tolerance. It skips that entire second loop. So resid store never changes its value. So before I get in there, I have to change the value of residual, kind of reset it so that residual is now greater than tolerance, and that second loop can run. Cool beans? So run that. Get one value out of it. Okay, that's cool. Not what I'm looking for though. What the heck? Why that happen? I got one value out. One value. And if you saw that value, what was it? It was. So in theory, that second loop has converged in one step. Yeah. The R value, right? Because the value of R is also something that's a carryover from this loop. When that first while loop finishes, R is exactly the right answer. Exactly the right answer. So I need to reset that too, because else it just starts at the right answer and says, okay, I'm done. Next, and that's it. So I'm going to go up here. I want to get exactly the same value that I started out up here, because if I change it, it'll change the number of iterations that it'll take to solve. So I'm going to grab that value of R. I'm going to slap it down there. Let's try this again. Well, that's not good. What does that mean? Index 145 out of bounds for x is 0 with size 145. Right. It's trying to put a value into that array at an address that doesn't exist. In this case, it's address 145, and the size of the array is 145. Well, if the size of the array is 145, what's the largest address in the array? 144, right, because it always starts at 0. So it always has one less value in, it always has one less address in the array than the total number of places in it because it starts at 0. But that's weird because we made the array like exactly the right size, right? Like we counted up how many places there should be in it. We made the array that size. We started at exactly the same place in this new while loop. It should take exactly the same amount of iterations, right? Why the heck are we getting an out of bounds thing? So if we go down here, what address do I start at? Do I? Right, because counter starts at 0. Up here on line 34, I add 1 on line 41, making the first address I try 1.
So I need to move that counter so that's after the arrays. Now the addresses should start at 0. Let's try this one more time. That looks more better. So it looks like a whole bunch of residuals. And we know that it's not going for more iterations because because if it did, we'd end up with that same error again, because it would have tried to place one more value or more values in array addresses that did not exist. So we know that it's doing exactly the same thing that it did in the first while loop, and we're all set to go. Awesome. So now we need to plot that. All right. I always forget the syntax here, so I always steal things. 1 second, please. Fall 10. Select 9. Nope. 10. Yeah. Oh, nope. That one. Okay. I just on the left-hand side, I just pulled up a plotting example that I had, because I'm going to steal the syntax to plot from it, paste it into my new code, and call it a day. So got this. I was plotting two things before. I'm plotting one thing now. My x-axis is my the x-axis for convergence history. I want to be a iteration number. I know that variable does not exist. And the y-axis, I want to be my residual. Label them appropriately. So the x label would be iteration number. Y label would be residual. I'm not going to bother with the title. All right. So I'm plotting the convergence history here. So if I look up at my last loop, I'm missing some stuff. Like I don't have a storage of something that stores my iteration number, right? And actually, if I look at line 44, it's the variable's radius stored. I'm storing a residual in it. So that's not any good either. So I need to put one more variable in here. I'm just going to make up one more here, call it iteration number, or iteration num, because I don't feel like writing. I'm going to store counter plus 1 in there, because my first residual is after my first iteration, right? So counter 0. Want to store that as my first iteration, not my 0th iteration. So put that in there. We all good with that? Okay, cool. So leave that there for another 30 seconds. All right, see what that does. And there we go. There's my residual, there's my iteration number, and everything seems to be hunky of the Dory variety. So there's my convergence history, or my residual history, if whatever you want to call it. All right. If I wanted to plot something else, I could put radius in instead of residual. If I wanted to, if I wanted to vary time or something like that, that is definitely something that I can do. The only trick, though, is that the same way that we said the while loop takes time to solve, we have to keep that in mind if we decide to change what time we're solving for the radius at. We have to let the while loops run before we can change the time and run to convergence. So if I wanted to put this inside of a second loop, meaning everything into a second loop, that changes time, I can do that, but I have to do something like this, where I just change, to change the time once, let everything run, then change it again, let everything run, and so on and so forth. All right. This isn't the complete answer to that. They have to do a couple other things on top of this, but it's more or less just bookkeeping at that point. Any questions? All right. Thanks for stopping by.